Hi everyone, welcome to this session about hacking HTTP2 and new attacks on the Internet Next Generation Foundation. It's been a great day so far. I hope you enjoyed this session. First thing first, a little bit about myself. My name is Nadav Avital. I'm the Application Security Research Team Leader in Imperva with more than 10 years of industry experience, mostly in hacking, web technologies, security technologies. I hold a BSc in computer science, and two things about myself, as you're about to see. I love experimenting with new technology, and I love to break stuff. Okay, some credit to the guys that participated in this research. Noam Azor, former application security researcher in my team, and two students, Alex Majdanik and Avichai Cohen from the Technion Israeli Institute of Technology. So today I'm going to cover some background and motivation to HTTP2 protocol. Then I'm going to explain a bit about the technology. I'm going to move on to the exciting part of the session is new attacks, and conclude with a summary and takeaways. So why do we need a new protocol for the internet? The problem with HTTP1 is that it is no longer suitable for modern web content. In this example, we can see a single request to the imperva.com site that is followed by 123 subsequent requests to all sort of web resources, with a total 2 megabytes of data being transmitted and 12 seconds loading time. So we have numerous problems with HTTP1. We have a large number of web resources per page, latency, head of the line, and redundant information that is being sent over and over through the HTTP request headers. So who uses this new protocol? Already today we see that major browsers, web servers, sites, and content delivery network already support this new protocol. So it's fairly common. I'm going to dive just a description about the technology in order for us to understand the attacks that are going to follow. So HTTP technology can roughly be divided into 4 components. First, the stream multiplexing, which allows multiple HTTP2 streams over a single TCP connection. We have a flow control, which allows the connection participant to limit the amount and the timing of the data over the connection. We have header compression to compress the information that is being sent in the headers, and server push mechanism that allows the server to push web resources to the clients even before they ask it. Now, the smallest data delivery unit is called a frame. Frame is actually a binary object that can contain headers, data, settings, and more. A stream is composed of multiple frames, and it represents a request and response duo. An HTTP2 connection is composed from multiple streams that are transmitted over a single TCP connection. Okay, so after we understand why we need this new protocol and how it works, it's time to see new attacks. So in our research, we tested 5 major web servers that count for most of the internet traffic according to Netcraft statistics. We tested the Apache server, Windows IIS, Nginx, and 2 more implementation of HTTP. 2 is NGHTTP2 and Jetty server written in Java. So we developed 4 different denial of service attacks based on zero-day vulnerabilities. All vulnerabilities are new and were found as part of our research effort to estimate the security posture of server implementation of this new protocol. All the CVEs were created by Imperva and were reported to the relevant vendors. Also, we worked together with the vendors in order to create the proper security solutions, which are now available through public security patches. So the first vulnerability is in the flow control mechanism. The flow control mechanism allows each endpoint in the connection to limit the amount of data that will be transmitted over the connection. And since it is mandatory by the protocol, servers that get such requests from clients must follow the request. And when we heard about this new data control mechanism, we immediately thought about data rate attacks. So we implemented a new low data rate attack to achieve a denial of service. And in fact, we reached the same effect of the famous slow low-risk attack over a single HTTP2 connection. So in this attack, first the attacker needs to open an HTTP connection and reduce the initial window size. Then the attacker sends a request for a large resource, bigger than the window size. And when Jetty server, for example, gets the request for a resource that is larger than the window size, the thread that handles the request goes to sleep for 30 seconds. In other servers like Apache or IIS, the attacker needs to keep the connection alive, and you can do that by slowly increasing the window size. And by sending multiple requests, the attacker can actually make all the threads that handles the request go to sleep and achieve a denial of service. And as I mentioned, all of that is done through a single HTTP2 connection. So we have a video demo. We have 3 players in this video. We have the Jetty server. We have a control client written in Python to send and receive responses from the server. And we have the attacker. Now the attacker launches the attack, and a few seconds afterwards we can see that the control client stops receiving normal responses, gets all kind of errors, and then the attacker stops the attack. And after a few seconds, we can see that the server slowly begins to recover, and the control client will resume receiving the normal responses. Okay, moving on to the second vulnerability. The second vulnerability is in the stream multiplexing mechanism. So multiplexing addresses the latency and head of the line problems by allowing multiple requests and response at the same time over a single connection. However, the partition of the TCP connection is purely logical, and as such it can be manipulated by an attacker to send frames and streams out of context. So the attack flow is very, very simple. In fact, it's sadly simple. And in this attack, the attacker opens an HTTP connection and sends 2 requests on a single stream. So in this case, we tested the Windows IIS server, and not only did the IIS server crash, we also got a blue screen of death. Yep. And of course, denial of service. So here's the demo. We've got an IIS server running on top of Windows 10. We've got a browser, which is our control client. And we've got the attacker. And the attack is very short. And as you can see, blue screen of death. Now the third vulnerability is in the header compression mechanism. The header compression mechanism reduces the bandwidth by compressing HTTP2 headers. And in this mechanism, both sides, client and server, maintain a header table per TCP connection direction. We have one table for incoming requests and another table for outgoing responses. And this table consists of dynamic part and static part. And the client and the server use these tables in order to, as dictionaries, in order to compress and decompress the headers. So for example, we have on the left, we have a full representation of the request headers. And on the right, we have the compressed representation for the same headers using the compression table in the middle. So we can see that for some of the headers, for example, the get method header, we have a single byte reference representation in the compressed table, in the compressed representation. So in this attack that we call an HPAC bomb. HPAC is the algorithm for the compression. We abuse the compression mechanism in order to inflate the server memory by a factor of 4,000. So the attacker opens a connection and first inserts a long header to the dynamic table. We call it header X. Then the attacker sends a request with thousands of references to this header. And by doing so, it inflates the server memory. We have on the attacker side 16 kilobyte of memory that it needs to invest in this request, and it decompresses on the server side to 64 megabytes. So by sending 14 compressed frames, we were able to crash the server. So this is the math. We have the default size of the dynamic table is 4 kilobytes. And one request can contain 16 kilobyte of headers. Now reference, as you previously saw, reference it can take 1 byte. So we can actually send 16 kilobyte of references. That means that a single request can be decompressed into 64 megabytes. And 14 requests will decompress into 896 megabytes, which was enough in our case to crash the NG-HTTP server. So in this example, we have the NG-HTTP server, and we monitor the server CPU and memory consumption. And we have the attacker that launches the HPAC bomb attack. And we can see that the memory and CPU consumption spike. The attacker keeps sending the compressed frames. At this point, the system monitoring halts. And after a few seconds, we'll see that the attacker gets failure responses from the server. And the monitoring, we see that the server process dies with a segmentation fault. So here's a funny story. NG-HTTP2 project also supplies a standalone libraries that are used in other products. For example, in Wireshark. So when we developed this attack and wanted to report it to the vendor and send a network traffic pickup file. So we recorded the attack and we played it in Wireshark. And what we saw, and we're very surprised to see that the Wireshark has the same vulnerability since it uses the library, the standalone library that is vulnerable. So we saw all these attacks, and the questions that comes to mind is, what can we do? So we have 3 options. First one is just to say, forget about it. Let's just abandon the plans for HTTP2. But HTTP2 is the next generation protocol for the internet, and it solves a lot of real problems in HTTP1. Also, we have a dozen of other vulnerabilities that are published every month or every day for non-HTTP2 servers. So this option is off the table. So we can also choose a secure server implementation, but in our research we found that no such server exists. So all the servers that we tested were found vulnerable for at least one of the attacks. And what about third-party software? As we saw in the example of Wireshark, perhaps the server implementation is secure, but third-party software that are on the server are not secured. And even if you can find a secure server implementation, more vulnerabilities are going to come. And in fact, since the time that we published the report, dozens of more vulnerabilities in HTTP2 were discovered and reported. So we are left with the third option, which is to patch. And when you patch, you need to build a patching framework. And when building a patching framework, you need to ask a lot of difficult questions that some have answers, some may not have answers. Questions like, how do you know that a vulnerability exists? When will the patch be ready? What's the impact of the patch? Is it stable? So sometimes vendors are rushing into things and publish security patches in order to satisfy a customer's demands without properly checking them. So let's look at another approach where the application is equipped with a web application firewall with virtual patching. So the traffic is monitored by the web application firewall, which can be either on-premise or in the cloud. And when a security flaw is detected, is found in the web server, virtual patching is deployed in the web application firewall and stopping attacks at the web application firewall instead of the server. So the server remains intact and protected. No need to change anything in the server. And the application owner can actually focus on business instead of focusing on building a patching framework and answering all these annoying questions. So the key takeaways from this session. HTTP 2 is great. It is here to stay and rightfully so. But it also extends the attack surface for web attackers. We have new and highly customizable transport mechanism, a new amount of code that was released in a short amount of time. And we need to remember that HTTP 2 is still uncharted territory. So, and HTTP 2 ecosystem is still not security mature, unlike HTTP 1, which is with us for 20 or 30 years, right? So we have a lot of researchers, we have a lot of implementations that are fairly secure. And things may even, for HTTP 2, things may even get worse when servers and sites will start utilizing the full capabilities of this new protocol. So right now, what we see is that there is like a sort of a transition period. So sites are using this protocol, but they are not fully utilizing the capabilities. And the last key takeaway is that without an external protection and virtual patching, it will be very difficult for business owners to win the patching race. So this was my last slide. If you want to read more about the technical details, you can get it in the following URL address where we publish the report. And we have some time for questions, so thank you. Yes.
During your test, did you have the feeling that the protocol is vulnerable or the implementation is?
So yeah, the question was if during our research, if we found that the protocol is vulnerable or the implementation. So our research was, we concentrated our research at server implementations. Yep. Yes. Sorry? Yeah, so I was instructed not to pitch any product. No, we didn't test web application firewalls. We tested web servers. But of course, if you want to choose a web application firewall, you should choose one that is capable of protecting from HTTP 2 vulnerabilities. Yes?
Did you guys publish tools that you used for these attacks?
No, we did not publish tools, but the attacks are very, very simple. And all the technical details are in the report, so it's fairly simple to build the attacks. We did all of the attacks were created with Python scripts. Yes.
Some languages natively implement HTTP2. Did you test the web servers providing, like for example, Node.js or Golang? Those are natively implemented into the language. To test this?
So no, we did not test it. I know that was a discussion in some of the communities that after we published the report, people started asking questions. Is Node.js vulnerable, yes or no? I didn't follow up on that, but the simple answer is that we didn't test those. Yep.
Most of the attacks that you learn it can happen because normal usage because some browser decides to send a large header or something like that. There's a way that the firewall would translate those trouble messages as something that a server can understand. So it won't destroy the connection or something like that?
I'm not sure I fully understand your question, but from the question was some of the attacks may look like normal.
Maybe legit requests that are big problematic.
So it's very hard for me to imagine that any of these attacks will come from legitimate clients. I mean, to create 16,000 references to an entry that consume all of the compression table is not something that you would normally see in web traffic. Anyone else? Okay, thank you.